What do you think it means by right triangle trigonometry? What does a right triangle mean? What does it look like? Yep, 90 degrees. A right triangle, by definition, is one that has 90 degrees as one of the corners. Then we have two different angles here. Are they always going to be different? No, but if one's 45, the other one could be 45. What is the sum of the internal angles of a triangle? Yeah. So here we have, we'll call this A, call this B, and call this C. The angles A, B, C, and a triangle has to equal 180 degrees. And one of them, since one of them is 90 degrees, then we have A plus B equals 90 degrees. If this angle C is 90, that means these two other angles have to equal 90 degrees. That's got a name. If two angles, angle A and angle B, add them together equal 90 degrees, what's that called? Nope. They're complementary angles. Students get mixed up with these terms, complementary. The other one that we'll eventually talk about are called supplementary angles. Complementary is A plus B equals 90. Here we have two angles that equal 180. Now, I'm going to show you the highly technical mathematical way I remember the difference between the two. The number of p's. Each p is worth 90 degrees. Complementary only has one p, so it's 90. Supplementary has two, so it's 180. That's how I remember it. Now, the reason we use right angles is because once I define a side, once I know two of the three sides, I can figure out the third one. How? Pythagorean theorem. The sum of the square of these are called legs. This is leg A, and this is leg B. The C is called the hypotenuse. Hypotenuse. So the sum of the square of the legs is equal to the square of the hypotenuse. And any algebraic manipulation thereof. How are these sides and angles? Because we have points, we have vertices here. How are they labeled? If this is side B, then this one has to be point B. It's always the opposite. If this is side A, then that has to be point A. And then this is point C because it's opposite hypotenuse. This is going to be important for the next two sections. We're going to do side, angle, side, angle, side, angle, side, side, side. Also, using our SOHCAHTOA formula, remember what that means? Sine of theta is equal to the opposite over hypotenuse. Cosine of theta is equal to the adjacent over hypotenuse. And tangent is equal to the sine over cosine, which is the opposite over the adjacent, because the hypotenuse cancel. This is a typical 3, 4, 5 triangle, because if we plug these into the Pythagorean theorem, it works. So, since I said the sine of theta, what would the exact value be? Here's theta. What's the opposite of theta? 4. The hypotenuse is 5. The cosine of theta is the adjacent. It's the side touching that angle over the hypotenuse. The tangent is the opposite, which is 4, over the adjacent. So it's all relative to where what you're looking at, what angle you're looking at, because sine of phi, it now changes. SOHCAHTOA doesn't change, but what's adjacent, what's opposite changes. So what's my sine of phi going to be? Yeah, it's opposite, which is 3, and the hypotenuse is still 5. Cosine is going to be the adjacent. And the tangent is going to be the opposite over the adjacent. So depending on which angle is being specified, that will dictate which sides, what lengths you use. So far, so good? How many trig functions do we have? We have 6 basic ones. We actually have a couple of hundred because we have the hyperbolics, we have the inverses, we have the inverse hyperbolic, we have a whole bunch but the 6 basic trig functions. We have the 3 basic ones we begin with. You're still writing? Go ahead. No. If I flip the page too soon, tell me. We'll all just sit here and stare at each other while you're taking your time. Good. You sure? So we have the 3 basic ones, which is sine theta, cosine theta, and tangent theta. Then we have the reciprocal ones. We have the cosecant, which is 1 over sine, which is the flip of the sine function. We have the secant function, which is 1 over cosine, which is the flip of the cosine. And then we have the cotangent, which is 1 over tangent, which is the flip of the tangent. They're just reciprocal functions. Example 1. Find the 6 trig functions, the exact values. Relative to theta. Actually, hold it. This is too easy. There. Because we knew the other one was 3, 4, 5. Let's do this one. So what's this side length? Let's see. So we have a squared plus b squared equals c squared. 5 squared, we don't know what that one is. We know that's 6 squared. So we have 25. 6 squared is 36. So b squared equals 11. B equals plus or minus square root of 11, and you can't have a negative side. So square root of 11. So the sine of theta is, here's theta. The opposite is square root of 11 over 6. The cosine is the adjacent over hypotenuse. The tangent is the sine over cosine, which is the numerators. Cosecant is simply the flip of that one. Secant is the flip of this one. And cotangent is the flip of this one. So actually, you see, all you have to do is find sine and cosine. Once you find that, everything else falls in place. Because everything is a function of sine and cosine. Everything is a function of x and y. So far, so good? We'll do that one next part. We're going to do application problems next time. use the what is the complementary angle? We just talked about those earlier. What's a complementary angle? Two sides that add two angles that equal 90 degrees. Whose sum is 90 degrees. So we'll call this one A, we'll call this angle B. Let's look at this. So sine of angle A is what? Here's angle A. A over C. What's the cosine of B? A over C. The sine of B is B over C. That's also the cosine of A. Those relationships have a name. Cofunction. Because of how, with respect to which angle you're looking at, we'll get the same answer. So the sine of alpha A is the cosine of B. Those are cofunctions of each other. Does it work for all of them? We did sine and cosine. How about tangent? Tangent of A tangent of A is what? Is opposite over adjacent. What is that equal to with respect to B? Adjacent over opposite. The cotangent of B. Sine and cosine are cofunctions. Tangent and cotangent are cofunctions. And what else? What else cotangents would be? Or the last pair? What is the secant of A? What is it? Because it's, remember, it's 1 over cosine. Cosine is adjacent over hypotenuse. So it's opposite hypotenuse over adjacent. So it's C over B, which is the same thing as the cosecant would be. Let's look at this now. Another way we can look at this. Because remember, we have A and B. If this is a right angle, That means A and B, if I add those two angles together, what do they have to equal? So whatever value I put in there, let's say secant of 20 is equal to the cosecant of what? Because both of these have to equal 90 degrees. They have to be complementary to each other. So cofunctions work with complementary angles. Sine of 1 degree is equal to the cosine of 89 degrees. Because the two angles have to add together to give you 90 degrees. Example 3. Use the complementary angle theorem. So what does this equal? Cosine of what? How'd you get 28? -90 minus 62. How about the tangent of pi over 12? It's going to follow the same logic as this. This one, since we're dealing with degrees, I use 90 degrees. Here I'm using pi. What is the pi angle of 90 degrees? Right. So it would be cotangent of pi over 2 minus this angle. So it's cotangent. Get a common denominator, so it's 6 times 6, so it's 6 pi over 12 minus pi over 12, which makes it 5 pi over 12. So that's the complementary angle to that one, or the cofunction also. Sine squared 40 plus sine squared 50 degrees. What would this equation equal? Why? Sorry, I can't hear you. Sorry.
sine 40 equal cosine, no, is equal what? Cos 50. So when you raise, it's going to be
Y is equal to 1. Why is it equal 1? What's the formula?
cos squared.
Right. Are they the same angles? Oh yeah, because we're gonna look at this two ways. Right. It's gonna equal 1. Because the cofunction of sine squared of 40 is what? I could leave those together. So cosine squared plus sine squared equals 1. I could change this one. Or I can change this one. I could have sine squared of 40. The cofunction of sine squared of 50 is cosine squared of 40. Since they're both the same angles, cosine squared plus sine squared equals. As long as the angles are the same. So we could do either A or B. We're given this one, so we can find the cofunction of sine of 40, which is cosine of 40, or cosine of 50. So cosine 50, sine of 50 is equal to 1. Or I could take this one. What's the cofunction of sine of 50? Cosine of 50. So, or 40. So now those are the same angles. Solving right triangles. So we have A, side A, B, side B, C, side C. So what formulas do we have so far we talked about today? We've used a lot. Whenever you deal with right triangles, you always deal with Pythagorean theorem. And we also dealt with complementary angles. We'll only need this information. Let's look for example here. We only need this information to solve what we're looking for. So if B equals 2 and A equals 40, find A, C, and B. Because if you think about it, if we have a right triangle, how many unknowns can we have here? We know this angle, right? This one's got to be 90. So that matches with the hypotenuse. This is unknown. This could be an unknown. And the lengths of the sides. So we could have 5 unknowns. But we need to know, besides the 90 degrees, we have to know 2 more pieces of information in order to solve for the rest of them. we got two pieces of information here. So out of this equation, B is 2 and A is 40 degrees. So can we figure out any of this stuff so far? What's B gonna be? Has to, yeah. Because A plus B has to equal 90. So now we gotta figure out a and little c, the side lengths. How are we gonna do that? All we have is this side here. Since we're given 40 degrees, let's use this angle. So what formula can we use with this one to figure out A and C? Is this adjacent, opposite, or hypotenuse to A? So it's adjacent. So which functions deal with the adjacent function? We know one adjacent over hypotenuse. What's that? That's cosine. What's another one? So here we can figure out the hypotenuse using cosine. How do we figure out this one? A is what? Opposite over adjacent. If we do that, then we use tangent of alpha. So that's A over B. This one is B over C. So the cosine of 40 degrees is equal to B over C. How do we know what B is? So if we multiply both sides by C, we got 2 equals C times cosine 40. C is equal to 2 divided by cosine 40. We just found C. Likewise, if we have tangent of 40, A over 2. So side A is equal to 2 times tangent of 40. Plug those in the calculators, and there we have the sides. This is how you would use the trigonometric identities of the functions, the equations, to figure out other sides of a triangle. Yes. Yes, you have to be in degrees. All right, let's look at example 5. Is that the only way we could have done it? Is that the only way we could have done it? Do you know any inverse trig functions? Have we discussed any of those? So no, you couldn't. Because you heard of them, do you understand them? Do you know what they mean and how to get them? So, yeah, so I said, no, use only what you know. Because if you start going up in the deep end, who knows what's down there? Instead of cosine, can we use sine? we could use sine of B. Since we know that this is 40 degrees, that has to be 90. This one has to be 50. So we could also have done sine of 50 is 2 over C. So yeah, there are many other ways you can do it. But as long as you use what you know, you have to have your unknown has to equal something that's known. We just plug the calculator in, cosine of 40. What do you think cosine of 40 is anyway? How would you guesstimate cosine of 40? We have our unit circle. Halfway is 45, so 40 is, let's say, right about there. Cosine deals with which axis? Cosine deals with the x-axis. So if we go from this point where it touches a circle straight down, remember, it stops at 1, starts at 0. What number do you think is approximately there? What number do you think is there? So here's 5, 6, 7, 8. So we're at 7.7. This is how you would guesstimate what the answers are, what the numbers are. You know it's bigger than 0.5. It's smaller than 1. So it's around 0.7 something. So if you don't have a calculator, you don't have to worry about it. You can always guesstimate it by looking at the cosine deals with whatever the angle is, where it touches the unit circle, down to the x-axis. The sine value goes onto the y values. So here's 0.5. So that one's probably closer to 0.6, between 0.6 and 0.7. You have to know how to guesstimate to see what the answers should look like, because you won't always have your calculator or your phones with you. Solve right triangles. If A equals 3 and B equals 2, find C, A, and B. And which we're going to be. Let's first make sure everybody's on the right picture. This is our C. So if we call this A and we call this B, where's angle A? Since this is A, angle A has to be over here. It's always opposite. And then this has to be angle B. So first thing, easiest thing to find is C. How are we going to find C? Yeah. So we have 3 squared plus 2 squared equals C squared. So C squared equals 13. So there's my value of C. Can we find the angles now? Let's find angle A first. So what we know for sure are these two numbers. What equation do we have that we can use the opposite and the adjacent? Tangent of A is opposite over adjacent. So what we're looking for is we're trying to find what angle makes the tangent equal to 3/2 or 1.5. We got to get rid of the tangent. That is where the inverse comes in. Inverse tangent times tangent is the angle. We're trying to find the angle that makes, because 3/2 is not an angle. When you deal with imaginary inverse functions, that's what this -1 means, inverse. What this is asking us is what angle equals tangent of the sides? What angle makes the opposite over hypotenuse that value? Unfortunately, here, well, we could try to figure out if we have 3/2. This will be horizontal. So approximately what angle is that? It's got to be just a little bit bigger than 45 degrees. So let's say A is approximately 50 degrees. If you had a calculator, you can just type it in there. But again, if you don't have a calculator, you would just approximate those numbers. Because remember, tangent is sine over, it's the height. It's the y value over the x value. So up 3/2. What is that angle? It's about 50, 55 degrees. How about figuring out B? Which one can we use here? Can we use tangent again? Tangent of B, opposite over adjacent. Which you go up 2/3, which is just a little bit lower. It's lower than the 45-degree angle. So, well, if we know this one, can we calculate B automatically? Yeah, because I have to equal 90. So if that's 50, then B has to equal 40. Right. So that's the beauty of using any of our formulas that we have. As long as we have them, we can use them. Applied problems. This will suck up most of our time. So here's our first one. A surveyor can measure the width of a river by setting up a transit at point C on one side of the river and taking the sighting of a point A on the other side of the river. Refer to figure 10A. So here's the picture there. That's what it's saying. So once he figures out this, he can calculate with the degree angle. Same point in the survey. After turning through an angle of 90 degrees at point C, the surveyor walks a distance of 200 meters to point B. Using the transit at B, and the angle theta is measured found to be 20 degrees. What is the width of the river rounded to the nearest meter? So let's look at the picture. So here we have a river. That's where he set it up. This is point B. This is point C. We know that it's 200 meters. That's point A. And we know this angle here is 20 degrees. So how are we going to solve this? We know that's 20 degrees. We know this. We want to know the width of the river. So what function are we going to use? We're going to use tangent. Angle is 20. The tangent is opposite over adjacent, which is B over 200. So the width of the river, multiply 200 to both sides. Get your calculators out. What we're going to get sine of 20 over cosine of 20, but use calculators here. It'll save you a bunch of time. What'd you get? 72 point what? 72.8 meters. But 215 feet. Pretty wide river. All right. Example 7. Example 7. Finding the inclination of a mountain trail. A straight trail leads from an alpine hotel at elevation 8,000 feet to a scenic overlook elevation 11,100 feet. The length of the trail is 14,100 feet. What is the inclination grade of the trail? In other words, what is the angle from the horizontal? We know that the height is 11,100. The distance traveled is 14,100. What is the angle B? So let's see what we have here. From the horizontal, we know that the trail is 14,100. The hotel is at 8,000 feet. And the lookout point is at 11,100 feet. So do we know this distance here? At 8,000 to 11,000 is what? From 8,000 to 11,100. From 8,000 to 11,100 is 3,100 feet higher. So what formula are we going to use here to find B? What formula first? We set it up. You're missing the whole middle point. What you have to set up the formula equation first. So we have the opposite hypotenuse, which is sine. So we have sine of B equals the opposite, which is 3,100 over the hypotenuse. You always have to set up the equation before you try to solve it. Now, since we're looking for the angle, we have to move that over. So it's the inverse. The zeros cancel. So it's 31 over 141. Approximately 12.7 degrees. So it's a 12.7 degree incline. So yeah, once you have your picture and you start labeling the pieces that you have, then you can come up with an equation, and then you can use whatever inverse or whatever you're looking for. But first you have to start off with the basics. A diver is on the jumping board. The scoreboard is up here. The audience and the judges are down here. If you're looking up as opposed to looking down, What's the difference in the terminology? Yeah, this is the angle of elevation. And if it's going down, it's the what? What's the opposite of elevation? Depression. So it's always referenced to the horizontal. If you're looking up, you're elevating. If you're looking down, you're depressing. So example 8. Yeah. Yeah, the angle of depression is going down. So meteorologists find the height of a cloud using an instrument called the ceilometer. Ceilometer consists of a light projector that directs a vertical light beam up to the cloud base and a light detector that scans the clouds to detect the light beam, as seen below. At Midway Airport in Chicago, the ceilometer was employed to find the height of the cloud cover. It was set up with its light detector 300 feet from the light projector. If the angle of elevation from the light detector to the base of the cloud was 75 degrees, what was the height of the cloud cover? Ah, it's a lot of info. So what it says, to find the height of the cloud cover. We want to know how high it is. So if it was set up 300 feet from the projector, that's the base. Find the angle of elevation of the light if its cover is 75 degrees. So here we have, it's on the horizontal. That's the beam straight up to the cloud. So this angle was 75 degrees. The distance from between the instruments was 300 feet. We want to know the height. I've always wondered how they did that. So what do we have? What do we know? What are we looking for? And what function are we going to use? This, we have the angle. We have, this is what compared to this angle? Adjacent. And we're looking for the opposite. We're going to use the tangent formula. Tangent of 75 degrees is the opposite, which is the h, over the adjacent, which is 300. Solving for h, we multiply 300 both sides. So the height is 300 times tangent of 75 degrees. That came out to be approximately 1,100 feet. So the cloud base is at 1,120 feet. Okay. Any questions so far? How about number 9? Finding the height of a statue on a building. Adorning the top of the Board of Trades building in Chicago is a statue of Ceres, the Roman goddess of wheat. From the street level, 2 observations are taken 400 feet from the center of the building. The angle of elevation to the base of the statue is found to be 55.1 degrees. And the angle of elevation to the top of the statue is 56.5 degrees. What is the height of the statue? Well, this is what it's saying. We're 400 feet from the center of the building. From where you're standing to the bottom of the statue is 55.1 degrees. To the top of the statue is 56.5 degrees. We have these 2 different pictures. We have the first, this is to the bottom of the statue, this is to the top of the statue. The difference of these 2 is going to be the height. So what function are we going to use to solve for it? Yeah, because we have opposite and adjacent. So we'll use a tangent for both of them. So we have this is 400 feet. The lower one is 55.1 degrees, and the outer one is 56.5 degrees. So B1, this is to the base of the statue. Tangent of 55.1 degrees opposite over adjacent. So that's the base. Then the second one, the second observation was at 56.5 degrees. That's to the upper one over 400. So B2 minus B1 will give us the statue height. So we have 400 times tangent 56.5 degrees. That's B2. 400 times tangent of 55.1 degrees. Close. So this one is approximately 573.9 feet, or 0.39 feet. Let's say 0.4. And this one is approximately at 604.33 feet. So 604.33 minus 573.40. Approximately 31 feet tall. All right, let's look at example 10. The Gibbs Hill Lighthouse, Southampton, Bermuda. In operation since 1846, the Gibbs Hill Lighthouse stands 117 feet high on a hill 245 feet high. So its beam of light is 362 feet above the sea level. A brochure states that the light can be seen on the horizon about 26 miles distance. Verify the accuracy of this statement. Now, how does that relate to this picture? The Earth is round. So if this lighthouse on top of this hill is 362 feet tall, how far can this lighthouse be seen until the curvature of the Earth eats up the lighthouse? That's what we're looking here. We're looking for S. We're looking for the arc length. So how are we going to do this? Example 10. So we have the lighthouse is 117 feet tall. The hill is 245 feet tall. Light be seen 362 feet above sea level. The distance is 26 miles. So what do you have to do with this equation to get it working? How do we set it up? Which function are we going to use? We know the height here. Where's our angle? Because this is the base, this is the hypotenuse, this is how far until we get our points bearing intersected. So what do we do? What function are we going to use? No, that's just this distance here. The height of the tower from the hill and the tower. And from the top of the tower, you can see the light 26 miles. So from that tip of the light to where you can stop seeing it is 26 miles.
But we don't have any angle. They didn't give us any, right? Would we use Pythagorean just to tell them the missing stuff?
It's just asking us to verify the statement. But it does also tell us the distance of the Earth, the thickness of this Earth. 3960 miles. The radius of the Earth, yeah. Because from the center of the Earth to the core of the Earth is 3960 miles. So we have this one. We have this length. Actually, we know both of these. So which trig function we're gonna use? Since we want to know if it's possible. Which one? Sine would deal with cosine deals with the adjacent and hypotenuse. If you think about it, if we take the cosine, because we're asked to verify this, the cosine would take the adjacent and the hypotenuse, which would be this whole area distance here. And we were going to verify if this is a true number. So if we use cosine of the theta adjacent, which is 3960 over the hypotenuse, which is 3960 plus this 362 feet. What's wrong with this equation here? This is in miles, that's in feet. How do we convert them? $362 divided by 5,000. What's the conversion for that? How many feet? 280 feet per mile. The feet would cancel, so this would give us miles. So we have to convert from feet to miles. That's how you do it. So what would this give us? Yeah, we need a calculator to find this. Once we find that, then we could find like the inverse cosine of it, which would be the inverse cosine of that. So what would you get?
That's 0.34.
Yeah. Now, is your calculator on radians or degrees?
Yeah.
Change it to radians.
0.0058. You were supposed to get 26.
No. We're looking for the angle here. And then once we find the angle, then we can determine that. So we can say that we can use tangent and then calculate for the distance here, see how long it's gonna be. Yeah, but it's not in degrees. I mean, it is in degrees.
The median radians, so I'm trying to do
No, yes, it's gonna be, well, I was looking at this, because if you look at how the proportionality, this is 3900, 3900. This is just a small speck of 3900.
it.
It's one hundredths that much. So yeah, 34.34 degrees sounds about right. So we can figure out there, this is our angle. Let's say 0.34 degrees. How do we figure out the distance here? What will we use? But if we use sine, then we have to use hypotenuse. If we use the tangent, then we can use this distance, which is a fixed distance. So the tangent of 0.34 degrees is equal to the opposite over the adjacent. So it's the x which we're looking for over 3960. So 3960 times the tangent of 0.34. Hopefully it comes close to 26. Because all our units are in miles.
23.5.
Right.
That's actually, and it's interesting, because it's about the same answer I calculated S like arc.
Mhm.
That turned out.
Yeah, so 23.5. Whenever you deal with maritime, ships always look at theirs as nautical miles versus statute miles.
Mhm.
So and because it's less than 3 miles, depending on the atmosphere, the moisture, the evaporation of the ocean could actually, there are some places where you look at it, if the temperature's just right, you'll see the ships floating because of the mirage effect. Yeah, it's freaked people out. So they saw ghost ships floating in the air. Well, it's just the atmosphere changing the clarity of the vision. Okay, let's look at example 12. Finding the bearing of an airplane. What is a bearing? When you're taking the bearing of something, what are you looking at? Relative to where? From where the object is from the vertical axis. So the bearing is this one, for example, this one is 30 degrees northeast. This one, the bearing is 70 degrees northwest. It'll be west northwest. So it's going west, but just a little bit up. And that's saying it's always referenced to the vertical axis. So this one's saying a Boeing 777 aircraft takes off from O'Hare Airport on runway 2 left, which has a bearing of north 20 degrees east. What does that look like? 20 degrees east is where? North is this way, 20 degrees east. That's what's going that way. After flying for 1 mile, the pilot of the aircraft requests permissions to turn 90 degrees and head towards northwest. The request is granted. After the plane goes 2 miles in this direction, what bearing could the control tower use to locate the aircraft? So he takes off from 2 left. When you read information on airports, runway 2, it's actually going at 20 degrees. So it's heading from north degrees, it's heading 20 degrees. So it's just taking off straight up. Its bearing is 20 north. After 1 mile, let's look at this. So after 1 mile, the pilot of the aircraft requests permission to turn 90 degrees and head towards northwest. So after you're going this way, after 1 hour, turns 90 degrees. After 1 mile, turns 90 degrees. And head towards the northwest. So it's not there. He wants to head this way, that 90 degrees. He wants to head north and west. That's granted. So now after 2 miles, we're using this as 1 mile. That's a mile. That's 2 miles. What bearing should the control tower use to locate the aircraft? So what bearing from the airport is the aircraft? So it should be last one. How would I figure it out? What do I know so far? This is the length of 1. This is the length of 2, because it went by miles. What is this bearing now? How do I figure that out with what I have? Is it a right triangle? There's the 90 degrees. This angle here, how'd you figure that out? Well, 20 degrees was right here. That was 20 from the airport. You went 20 degrees northeast for 1 mile, then turned 90 degrees. So now for 2 miles. So this is going to be further than that. We know this length. We know this length. We just have to figure out this angle. Which ones deal with, do we have the hypotenuse? No, all we have is the adjacent and the opposite. Which one does that deal with? Tangent A equals opposite over adjacent. Opposite is 2 over 1. what's that gonna give us? Because once we get this angle here, this is A. That's all of A. Once we get A, we subtract the initial 20 degrees, and that'll give us the bearing that the pilot's going next. So what is the inverse tangent of 2? What's that? 0.410?
Yeah.
63 point, what? Yeah. You're in radians. That sounds awfully small. So the angle, the angle alpha is 63.5, approximately there. So that's 63.5 degrees from our initial takeoff direction. We subtract 20 degrees. Because remember, we have bearing is always taken from the vertical north. So the airplane is at a bearing of 43.5 degrees north-northwest. So we have north 43.5 degrees west. If it's going south, then we put south 43 point where east and west. So this is how you read airplane charts. All right, that does it for that one. That one took a lot longer than I expected. The next two are going to be easier. We'll deal with the laws of sines and laws of cosine, and those are just plug and play the numbers like we just did here. Sorry about that, everybody.